So, we move on to the next section, which is on transport of pollutants. So, our general idea here, transport of pollutants, our goal is still the same, what we have been discussing right from the beginning, the overall scheme of things is to be, our objective is to estimate the concentration rho A1, rho A2, WA3, any of these in the environment under a wide variety of scenarios. Okay. In other words, we are just interested in finding concentration, because concentration is the main quantity that we are interested in terms of exposure. And so, from the chemical moves or pollutant moves from a source to a receptor, what happens to the concentration? Does it change? How does it change? Can we predict it? Can we measure it? These kind of things. Okay. So, primarily we are looking at modeling of this pollutant transport mainly, and then because we have a model, we must be able to validate models. So, we will use measurement techniques that we learned, adapt them to do this in terms of this. So, when we look at transport of pollutants, we look at a very simple scenario first. Is a river. Now, we'll before the river, the simpler system is a lake. Okay. You take a lake. The lake is a fixed volume. There is a fixed volume in the lake, and let us say that there is a chemical of concentration rho A2, which is well mixed. So, when we say it is well mixed, we are obviously we are assuming that the concentration is uniform. Okay. So, if it is well mixed, and let us assume that it is mixing, we will not worry about it how it is mixing. Let us assume it is mixing, which means the concentration is always uniform. Now, if I want to predict, this is a fixed volume, there is no flow of water, there is no flow and no flow of water outside, which means that this is fixed volume. If there is a chemical inside here, what is likely to happen to the chemical concentration here? So, if I want to, the question that I will ask is, what is rho A2 at some time t? Now, in this problem, the concentration of A in this water will only change if it is going away from the system, if something is adding or getting lost from the system. So, we invoke our overall mass balance, we invoke the mass balance of A in the system. So, if many of you have done mass balance before, the general this thing's rule, the equation for mass balance is the rate of accumulation equals rate in minus rate out. This is the general term. Now, rate in minus rate out can be in different forms. Okay. So, here the rate in, when we are talking about many general systems, we have different possibilities as follows: rate in by flow, rate in by other process, rate of this will pretty much cover lot of processes, general processes. Okay. So, in this particular system, lake system, there is no rate in by flow, there is no rate in by flow, there is no rate out by flow, because everything is in the river, in the lake, normal conditions, normal conditions. The rate of generation or rate of addition into the system by some other format, some other process. So, this rate of generation, the rate of generation could be by reaction, which means it is forming by reaction from some other thing, or it is coming, is transfer, that is occurring by mass transfer. And rate of loss also can be reaction and mass transfer. Mass transfer means it is going out of the system, not with flow, by some other means, by evaporation or by it is accumulating onto the walls of the lake, solid. The same way this gaining into the system is, it is transferring from the sediment to the water, or it is coming from air into the water. All these are possible. So, this entire mass balance system is written this way. So, generalize the mass balance, the general mass balance again. So, generation and loss. So, there is a sink, there is a reservoir and there is a sink, there is usual terms used for that. Okay. So, this is a general equation you apply to any system. So, what we define as a system is our main this thing. So, the rate of accumulation here in the lake, for the lake, the rate of accumulation, what is the rate of accumulation? The question is this: rate of accumulation is if the this rate of accumulation exists only when the system is unsteady state. Unsteady state. What we mean by unsteady state is the concentration is changing. So, each term in this equation, mass balance, has units of mass of A per time, it has units of rate. Every term in this unit has rate, is a rate term, m by t, ma by t. So, the rate of accumulation in unsteady state means it is dA 2 by dt multiplied by V2. So, these units are here. So, rho A2 is mass by volume, B2 is volume, and so this unit is this L cubed into Ma by L cubed into time. So, it is mass by time. So, for the lake this is 0, this is 0, and this rate of generation, rate of loss could be anything. So, if you know what is the rate at which loss or generation is occurring, that particular process you have to put that equation here. Okay. So, it could be anything. Say if it is reaction, rate of generation is reaction, and this is evaporation. Let's say this is evaporation. So, I need a term. So, now this rate of generation minus rate of evaporation. So, we have we will call it as R reaction minus R evaporation, which also should have units of mass by time. So, you have to look for individual expressions of these two terms, which comes from other domains of knowledge. So, you know the reaction, you know what is the reaction rate system, then the entire thing will come here, okay. First order rate, second order equation and third order. So, the overall sign of these things will be there if there is accumulation, which means if there is an increase in the concentration of A in the system, this will be positive, the left hand side will be positive. It will only be positive if, say, the rate of generation reaction to formation of A is more than the rate at which it is losing. So, the signage is important. It could be either way, it depends, this sign of the left hand side depends on what is happening on the right hand side, right. For example, if we take evaporation only, so the only process occurring is evaporation, there is nothing else, no reaction. Let us say I have a solution of benzene sitting in a lake. We will take a simpler example. If I have a generation of benzene sitting in a beaker and I am mixing it, I am well mixed, the initial concentration is this much. If only evaporation is occurring, okay, this is minus is the rate of evaporation. The reason I put a minus sign here is that d rho A2 by dt, if I am measuring the concentration, if I measure the concentration of rho A2 versus time, I am going to start somewhere, and because it is evaporating, it is decreasing, yeah. So, if d rho by dt is negative, this is negative. The rate of evaporation, as we mentioned, is positive. Whenever we talk about rate of evaporation, I think this is positive. So, in order to make this entire quantity positive, we put a negative sign there. So, the general rule of thumb is this: if you have loss, if there is a decrease in concentration, you put a negative sign to the left of it to make that quantity positive. The right hand side is always positive, that is the convention. We will come to that the exact terms for rate of evaporation, rate of reaction and all that later. But this generally this is so this is for a unsteady state model, okay. Now, if you take the case of a river is long river, so you have a big section of river, water is flowing, and you may have you are interested in getting the quality of water at a given place. Now, here you may have different flows coming in from different things, okay. For example, people are releasing waste into water in a river, or you are getting sewage into river, or you may have a tributary that is coming and joining a river. Any of these things are possible. So, the concentration of this depends on what is coming here and what is coming here in each of these channels, and what is evaporating and things like that. So, when you write a mass balance, it can be for the entire river, but you also notice that if a material is coming here and there are 3 sections here, very difficult for me, there is a group of population which lives here and there is a group of population which lives here, okay. How will I model this system? For me, I need to know what is the concentration at this point, I need to know what is the concentration at this point, so that I need to know what is the exposure of this set of population versus this set of population. So, in order to predict and model this kind of systems, it is very difficult for me to do this if I have a long system as it is, okay. Here I want to introduce a concept similar to what we did in the earlier system, except that now it is a flowing system. And this concept is known as a box model, and we will come back to this river system in a minute. We call what is a box model. A box model essentially is, it is a box, so it is a 3-dimensional box. And it has a certain volume, it has let us call it as delta x, delta y and delta z, and in this volume there is a concentration rho A2 or rho A1, whatever, we call it rho A2 for the time being. the basic assumptions of the box model is that it is well mixed, the contents are well mixed, which means that whatever enters here and something will exit here, something can enter and something can exit, something can exit here, something can enter here, something can enter here, something can exit here. All these walls, things can enter and exit, do whatever they want, that is all fixed. But when it says well mixed, this concentration is uniform throughout, there is no gradient or there is no difference in concentration everywhere. So, this would what we call as this, when we call it as well mixed, we will use what is called as a completely stirred tank reactor or a mixed reactor, CSTR. This is the assumption that we make. Now, if you do this, we also add one more assumption here, because it is a flowing system and this, we have a flowing system. We also can make superimpose another assumption here, which we call it as steady state. It need not be steady state, but let us have another assumption, relaxing assumption called steady state. This is very useful in flowing systems because nothing is accumulating, everything is moving here. So, what can happen here is in a river, real river, a long river, something enters here and this concentration may be different from this concentration, may be different from this here. So, what can be happening is, let us say a chemical is entering here and it can leave, it can evaporate. So, the concentration is decreasing as it is going if no other addition is happening. Okay. So, how do you predict this concentration here? One way to do it is, if I assume that this small section everything is well mixed, in here I will model what is going out and what is getting out of this system into the next system, next box. If I model this as a series of boxes, I make my assumption that this is all uniform inside. So, it is easier for me to model if it is uniform in each box. Okay. So, at one box goes to another box and therefore, I can model it very much more easily. There are other ways to do this, we will get to that. In terms of, so here if you do a steady state system, there is no accumulation, rate in minus rate out. So, we add up all these things, we will say rate in equals rate out. So, we add up all the processes that are contributing rate in. So, here we will say rate in by flow equals rate out by flow and plus something else. Now, you can have rate of evaporation and we can call it as here rate in rate of generation. So, what is happening here is the rate is constant, in the sense there is the same rate that is happening. So, what is coming in is going out, distributing into 3 different things. Let us assume that there is no rate of generation, let us say only evaporation is occurring. So, what is coming in is now going out in as evaporation and none of these things are happening. Okay. This is being divided into these 2 streams, that is it, and the next one goes in, there is a different inlet concentration and again that will also go out. So, here this is my equation. So, if I put this in the form of this thing, flow is the flow rate of the chemical multiplied by the concentration, this inlet, equals what is going out now. The units of this is Q is volumetric flow rate. So, it is L cubed by T into MA by L cubed, this is MA by T, this will also be the same. Now, if you notice here this rho A2, this rho A2 is the concentration that is leaving the system, which is also the rho A2, which since I am assuming it is well mixed, it is the concentration inside this box. This is the basic assumption of a CSTR. So, well mixed box model. So, into this box model I can add other terms if I want, I can add other processes that are happening. The advantage in the box model, if I extend a bunch of box models, if I put a series of box models, there I may have rho A2 0, that is, and I may have rho A2 in, that is entering, and here I may have something rho A2 out, that is exiting the system. Yeah. In between there is a big difference between rho A in and rho A2 out. In between I am going through a series of individual boxes where something is happening, evaporation is happening. Yeah. There is also possible for me to model this in this as what is called as a plug flow reactor. The same thing I can do as a plug flow reactor. I can take small sections, instead of taking it like this, what I am saying is this is plug flow, it is going in this direction, there is mixing in one zone, but as it progress from one zone to another zone, there is a difference because it is losing material or reaction is happening or some such thing is happening. So, the reason box model is used in practical systems like the environment is that unlike chemical reaction engineering where plug flow is used for a different reason, but here it is useful because the characteristics of each box may be different. For example, if you take the case of a river, if you take the case of river Ganges for example, the river Ganges comes from somewhere in the hills, its gradient is like this, okay, and then as it comes down to the upper plains and then lower plains, it becomes like this. Here the velocity is very high until it comes here. The volume is low here, the velocity is high here. There is low volume, high velocity. Here high volume, there is lower velocity. The terrain, the nature of the bed of the river is very different in the upper reaches, and as we come down into the plains it becomes very different. The cross section of the river is very different, everything is different. So, and there are a lot of tributaries that join and there are a lot of cities that join and all that. So, it is very difficult to predict the quality of water throughout modeling the entire river as one. So, they will divide it into a lot of segments. Now, a river is flowing. It is very unrealistic to consider river as a well mixed system because what we consider as well mixed means there is backflow. I put something here, it goes forward and comes back. That may not be happening in a river to a large extent. So, a river, you may have a little bit of backflow because river may flow like this, but this scale of this convection is not very high. But I think a lot of times we do not have a choice, otherwise our computation becomes very, very difficult. So, they will generally break it up into this kind of system. So, the hydrodynamic state of a river or a water body or the atmosphere becomes very critical to understanding that in order to model these kind of systems. So, if we take the same system box model and go to the atmosphere, this becomes more this thing. So, a river is very nice, it is a well defined system. I know the width of a river, height of the water, I know the volume in each section, I know what are the tributaries coming in and all that. In air, much more difficult. You can imagine if I am looking at air on top of Chennai, there is no, I do not know what is the dimension of it, right. I have to assume some dimension. So, this is a much more tricky problem in atmosphere science doing, but people have to work on this and we will come to that. So, a box model is used like this. So, what we will do initially now is to, in the next few classes, I will look at one box model and the adaptation of a box model for water quality, which is a very popular model that is used in for oxygen balance. And then we will see the adaptation of box models in the atmosphere to look at, and then each of these terms that we look at, we will look at how it relates to water pollution and air pollution and how it relates to predicting concentrations downstream and all that, and the assessment and estimation of each of these terms individually in the mass balance. Okay. So, most of the systems that we study in the environment are, we consider them as steady state except things like lakes, where we know that no flow is coming, but lakes also you can't consider them as steady state in a certain period of time when water is coming in. So, water is coming in with some chemical and chemical is going out in the form of this thing, you have to treat them as separate episodes of this. Okay. Anyway, so the idea here behind this thing is you must learn to identify how to take up environmental system and put it in the format of a model, so that you can predict or estimate concentrations as a function of time or space. Okay. So, we will stop here, we will meet on Tuesday.